Hello everyone, it's Mr. Ray here with another lesson in grade 12 data management. We are finishing off our unit 3 where we're looking at different types of probability distributions. This is lesson 4, which is the final key distribution that we're looking at, and this is called the hypergeometric distribution, and it's a very important one, and we'll see why once we learn what it is. Now, the last distribution we learned was called the geometric distribution, and it was all about the probability of waiting for something to be successful or waiting for the first failure of something. So it was totally different than the other distributions we've been looking at, and unfortunately the name of the distribution, geometric distribution, and this one, hypergeometric, they sound like they should be related, but they're absolutely not. So when you're thinking about these two, try not to think that they have something in common, because they have very little in common, which we'll see. So I'm going to start off with the definition, which will hopefully get us going in the right direction. Hypergeometric distribution is a distribution involving a series of dependent trials, each with success or failure as the only possible outcomes. So if we stop there, so there's two parts to this. The part that was the second part, success or failure as the only possible outcome. Well, that sounds a lot like binomial distribution, and it is in that aspect. Where it differs from binomial, remember we used P's and Q's for the probability of success and failure, which basically implies that those probabilities to succeed or fail never change. And that is true with binomial distribution. With hypergeometric, this one, it's dependent. Okay, so what that means is covered in the second line. The probability of success changes as each trial is made. So, for example, if you have a deck of cards and you're trying to get a jack, well, if you pull out a jack on your first attempt, the first attempt, the probability of getting a jack is 1 out of 13, or 4 out of 52. But as soon as you take one of the jacks out, the next time you try to get a jack, your probability has changed to 3 over 51. So that's what this is all about. So you definitely will not have the ability to use little p, little q as your probabilities, because those probabilities are forever changing. This line here, the random variable, is the number of successful trials in an experiment. Okay, and that's exactly the same as binomial. And the calculations of probabilities generally require formulas using combinations. So every time we predict the probability of a hypergeometric distribution, it's all about the number of combinations, the combinations that allow this scenario to succeed versus over the total number of possible scenarios. So let's go down to the key concepts. There's not too many before we get into the examples. Hypergeometric distribution has a specified number of dependent trials. So there it is again, having 2 possible outcomes, success or failure. So it's similar to binomial in that respect. It's different in that respect. Okay, and here's the big formula for the lesson. And this one has more variables, or at least different variables for sure. You can't use P and Q anymore, like we've discussed. So there's actually 3 different variables. There's the X, which has the same value. It's the number you want your random variable to be. There's the R, how many dependent trials are you having? Like if you're drawing 5 cards, that R is equal to 5. If you're picking 10 members of a committee, R is equal to 10. N is the population size. So how many people could you possibly pick for that committee, maybe it's 25 people. Okay, so that's the total, basically the population size that you're able to draw from. If you're picking cards, that would be 52 because there's 52 cards in the deck. And A is the number of successes in the population. So that's not the probability of success, that's just the number of successes. And we'll see how we use that when we go through the examples. And like all the other distributions, there's a kind of a shortcut formula for the expected value or expectation. E to the x, still called the same thing. This time it's r times a divided by n, and those are the variables we just discussed. Okay, so it's basically a ratio. Okay, so let's go on, look at some of the examples that hopefully help you understand. Okay, a committee of 6 people is to be formed from a pool of a pool of 6 grade 11 students and 7 grade 12 students. Determine the probability that the committee will have 2 grade 11 students. Okay, so we're going to define a random variable like we do all the time, and that will depend on what we're trying to test here. Probability that the committee will have 2 grade 11 students. So the random variable will be the number of grade 11 students on the committee. So let's say that right up front. X is equal to the number of grade 11 students on the committee. Okay, and let's talk about the other variables. We can kind of read through here, figure out what these numbers actually mean. Excuse me. A committee of 6 people. Well, that's basically going to be our R value. That's like the pool we're picking. So that's 6 from a pool of 6 grade 11 and 7 grade 13. So together we have 6 plus 7 students that we can choose from. So our N value, our population size, is 13. We're picking 6 of those 13 for the committee. And since we're looking for grade 11 students, how many do we have of those? Well, we have 6 of those, so that's our A value. Okay, so it's important to be able to pick those values out, write them down for sure, because the formula we use will be using those. So now we want to find the probability that the number of grade 11 students is 2. So in other words, X is equal to 2, capital X. Okay, now a lot of small writing in this example, in this lesson, so hopefully you can read what I'm writing. So the first combination we're going to pick is the number of ways we can pick our 2 grade 11 students. So since we have 6 grade 11 students, which is our A value, it's going to be 6 choose 2. So 6 choose 2, and so that's the number of ways we can pick our 2 grade 11 students. How many ways can we pick our non-grade 11 students, which in this case is just grade 12? So what you do is, how many can we choose from? Well, you take, this is actually going to be N minus A. So 13 minus 6 will be the non-grade 11 students. So in this case, 7 grade 12 students. So 7 choose. And since we want a committee of 6 students, that's our R value, and we've already picked 2 grade 11 students, so we have 4 students left to pick that aren't grade 11 students. So it's 6 choose 2 times 7 choose 4, and that's over the basically this will be N choose R, 13 choose 6. That's the total number of all combinations of 6 students for this committee. Okay, so if you go back to the formula here, I know it looks a little bit daunting at first, but this first combination here is how many ways can we pick our successes. In other words, for this example, it was our grade 11 students, so it's we had 6th grade 11 students, we want to choose 2, 6 choose 2, times the non-grade 11 students here. So how many can we choose? 7. And we want to choose, out of those 7, we want to choose 4 to make our 6-person committee. 7 choose 4. So there's a subtraction here, but basically if you think of it logically, hopefully you're not doing this math every time, but you could if you want to. And then n choose r in the bottom, which is our total number of combinations. And for this example only, I will actually do each combination separately. So it's going to be 15 times 35 over 1716. Okay. So you do the multiplication division, you get 0.3059. Therefore, there is 30.59% probability that the committee will have 2 grade 11 students. Okay, and that's exactly 2. It doesn't mean 3 or more. It's exactly 2. Okay, you get that from equals 2, which came from the original question. We'll have 2 grade 11 students. Okay, so hopefully that's a good intro into this type of probability distribution. In this case, we're just looking for one specific value of the distribution. Okay, in this example, we'll actually be creating a probability distribution like we did in some of our other lessons. A 5-card hand is dealt from a standard deck of cards. Show the probability distribution for the number of hearts in the hand. Illustrate the distribution with probability histogram, and some other questions that follow from that. So let's start off with the probability distribution. And in this case, X is the number of hearts in the hand. It tells you that right away. X equals number of hearts in the hand, Okay, now in terms of values, we need N, we need A, and we need R. So it doesn't matter what order you write these down, whatever you think of first. So in this case, you're talking about a deck of cards. So you have 52 cards, so N is 52. Okay. Your R value is how many are you picking or choosing. So a hand has 5 cards, so R is equal to 5. And finally, the number of successes out of the population. You're looking for hearts, so that's 13 hearts. So A is equal to 13. Okay, so now we can build our distribution. So in the first column, we have number of hearts, which is our random variable. And then we have our probability of getting that number of hearts over here. So let's give ourselves some room. Okay, now in terms of possible values of hearts, well, you could have anywhere from 0 to 5 hearts. So we have to have a row for each of those. Okay, so let me do some lines here. It's going to get a little microscopic here, so maybe I'll zoom in a bit more than usual. Okay, so let's move that up. Okay, I'm going to have giant hands here, so don't be afraid. So I'm just going to show you the formula, and then I'm going to go right to the final answer. So it's always going to be this fraction or a rational expression here. So the first one, how many ways can we choose our hearts? Well, it's going to be A choose X in this case. So 13 choose 0, 13 heart. How many ways are there to choose 0 hearts from 13? That's what that is saying. And then for the rest of the cards, well, 52 minus 13 gives you the non-hearts, so that's going to be 39. Choose, and basically all 5 of them will be non-hearts. And the bottom is always going to be 52, choose 5, because we're pick number of ways you can pick any 5 cards from the deck. When you do that calculator work, and it really pays to have that combination function on your calculator. They also have online combination calculators. If you don't have a calculator that does that, that's equal to 0.2215. Okay, so that tells you the probability of having no hearts in a 5-card hand is 22%. Okay, so now we move up to 1. So basically what we're changing here is now we're choosing 1, so that it'll be 13 choose 1, and the number of non-hearts changes to 39 choose 4. So basically you're bumping that number up and that number down. Everything else stays the same. So 13 choose 1 times 39 choose 4 over, this doesn't change, 52 choose 5. That is equal to 0.4414. Okay, so hopefully you see the pattern here. Now we're choosing 2 hearts, 13 choose 2 times 39 choose, and now we're choosing, we're picking 2 hearts, so that means 3 non-hearts. Okay, and over 52 choose 5, that is equal to 0. Hold on one sec, let me just double check this number. Okay, that is 0.2743. Okay, so you can see the so the probability for getting 1 heart in a 5-card hand is pretty high, 44%, and then 2 would be 27%. So you can see it kind of looks like it's peaking at 1, and most likely it's going to keep dropping because this would be very rare to have 5 hearts in a 5-card hand. So if we keep going, if we want 3 hearts, that's 13 choose 3 times 39 choose, and now you've got 2 other cards to choose, over 52 choose 5. That is equal to 0.0815. And for 4 hearts, that's 13 choose 4 times 39 choose 1 over 52 choose 5. And this is dropping quite rapidly, 0.0107. And finally, getting 5 hearts, so it's 13 choose 5. So all 5 cards are hearts, and none of the 39 non-hearts are picked. 39 choose 0 over 52 choose 5. That's equal to 0.0005. So very, very low. Now, I'm not going to do it, but since this is all the possible number of hearts, if we add up these probabilities, we probably won't get exactly 1, but it should be very, very close due to, it'll probably be a little bit off due to rounding, but it'll probably be like 1,000th or 10,000th off, so no big deal. Okay, so the second part of this, let me zoom out a bit, zoom back in. Okay, so second part is illustrate the distribution with a probability histogram. So it's basically taking the numbers from this table and just showing it graphically. Okay, so we have on the horizontal axis, so for our x value, we can have 0, 1, 2, 3, 4, or 5. So this is number of hearts, which is basically what x is. And this would be the probability of getting that number of hearts. So what we do to do the vertical scale, we look at the highest probability, which is 0.44. So that basically means if we go up to 0.5, that should be enough. So 1, 2, 3, 4, 5. So this is 0.5, 0.4, 0.2, and 0. So now we just do our histogram. So for 0, we're at 22.22, so that's about here. So we do our histogram with that. 1 would be 0.44, so that goes up to about here. Here's our bar for 1 heart. 2 hearts is 0.27, so that is about here. For 3 hearts, it's 8 or 0.08, which is under here. So and then 0.1, 0.01. So these are extremely small. This is probably exaggerating how big it is, but I just want to show that there's something there. And then just to make it a little more pleasing on the eye, do a little bit of shading. Okay, and there's our histogram, and you can see very quickly graphically what this looks like, and that's what they're asking you in C. See, what does this graph look like? Now, when we do our next unit, we'll be talking more about the shape and the way the graph looks, but for this, we'll just say it looks like a bell curve. Bell curve would be like bell curve, but not symmetrical. So symmetrical would mean it's exactly the same on both sides. You can see it's a little higher on the left side and it dips down quite fast on the right, almost like an asymptote. Okay, and then part D, what does probability of x equal 5 tell you? Well, x equal 5 means that all 5 cards were hearts, and we kind of mentioned that as we did it. That's an extremely low probability, so what the fact that px equals 5 is 0.0005 tells you that getting 5 hearts is very rare. And in previous examples, we know that getting all 5 cards of one suit is called a flush, and we already looked at the probability of getting a flush in a previous lesson, but not calling it the hypergeometric distribution, but it really was. We just didn't know it then. Okay, and then E says calculate the expected value and explain its meaning. So we get to apply our new formula. E of x is r times a over n. So based on our values we have up here, that's equal to 5 times 13 over 52, which is equal to 1.25. And what that means is, on average, there will be 1.25 hearts in a 5-card hand. And obviously you can't have a decimal part of a heart, but this is the average, and that makes total sense because hearts make up 1/4 of the cards, and 1/4 of 5 is 1.25. So you probably could have answered that without knowing the formula, just based on common sense. So let's go on to some more examples. This one's a little similar to the one we did with the students. A 6-person jury is selected from a pool of 8 men and 10 women. Create the probability distribution for the number of women on the jury and what is the expected number of women on the jury. So very similar to the last question. We're going to do a probability distribution for this. So let's do what we did before. So in this case, our random variable x, now you're going to choose what x represents based on the question, okay? So it says probability distribution for the number of women on the jury. So that tells you x represents the number of women on the jury. It just as easily could have asked for the number of men. In that case, you change your random variable to the number of men. It's totally dependent on the question. Okay, so let's look at our variables. So I could start with n, the total population we're choosing from for the jury. That would be 8 plus 10, which is 18. And a, in this case, is the number of successes, which is the number of women, so that's 10. And R is basically how many are you choosing, and right there 6 person tells you R is 6. So when we do our probability distribution, so number of women, which is X, and then the probability of that many women on the jury. Okay, so what's the possible values of X? Well, it all depends on, first of all, R. Okay, R is 6, so 0 through 6. Now you have to be a little careful, not in this question particularly, but you could get a question where, say you had 8 men and 4 women to choose from. Well, in this case, the distribution, you couldn't possibly have more than 4 women, even though the committee was 6, okay? So for that case, you would only go from 0 to 4. So this distribution is either going to go up to your R value or the number for A. So it's possible that A could be less than R, just because maybe you have less women than the jury size. So just be careful with that. So it's not automatically going to go up to 6, but in this case it does. So I'm going to have 0, 1, 2, 3, 4, 5, 6. Okay, so again, this is going to be pretty microscopic. I apologize. But I want to be able to fit the table in this section, and so I will zoom in again, just like before. Okay, so for 0 women, the toughest one's usually the first one, just to get started with your formula. So you think about, well, how many different ways can I choose the 0 women? So, well, it's 10 choose 0, which is really just 1, but still put it in the formula just to be consistent. So 10 choose 0, and then for basically choosing the men, we've got 8 men, or in other words, n minus a, so that's 8 men left over. 8 choose, and in this case we're choosing all 6 people from the men, and that's going to be over. So we have a total, it's going to be A choose R, so sorry, n choose R, 18 choose 6. That's the total number of possible juries with 18 people. You do the math for that, we end up getting 0.0015. Okay, for 1 woman, we just remember from the last example, we're going to increase the 0 to 1, we're going to decrease the 6 to 5, because we're adding a woman, we're taking away a man. So 10 choose 1 times 8 choose 5 over 18 choose 6. That is equal to 0.0302. Keep going. 10 choose 2 times 8 choose 4. Two women, 4 men, over 18, choose 6. That's equal to 0.1697. And you can see the trend here. We're definitely going up. It's more probable to have 2 women on the jury than 1 or 2. And it's interesting to see when this peaks, because that will most likely be where the expected value is, around there. So keep going with 3. 10 choose 3 times 8 choose 3. So 3 women, 3 men on this one, over 18 choose 6. That's equal to 0.3620. So that's very, very likely to have that number. So for 4 women, 10 choose 4 times 8 choose 2 over 18 choose 6. That is 0.3167. So now you can see that the probability is sort of peaked at having 3 women, and now it's gone down a little bit. Not a whole lot, but you can definitely see that. So you expect these last 2 values would decrease even more. 10 choose 5 times 8 choose 1. So 5 women, 1 man. 18 over 18 choose 6. That's 0.1086. So definitely gone down. And then finally, for all women, 10 choose 6 times 8 choose 0 over 18 choose 6. That is equal to 0.0113. Okay, so you can see the probability distribution here. They didn't ask us to graph it, but you would definitely see a peak in the middle and basically decreasing. It looks pretty symmetrical around both directions. Not exactly, but close. Okay, so now you can actually use this probability distribution if the question said, what's the probability of having 4 or 5 women on the jury? You could just go down to these entries here, and since it's or, you just be adding these 2 probabilities together. So that's like close to 0.43, probably 43% for having 4 or 5 women. Or you could group it even more. You could say something silly like, what's the probability of having an even number of women on the jury? Well, you take the probability for 2, for 4, and 6 and add them together. So that's where you can really take advantage of having the distribution all made out for you. Okay, second part was, what's the expected number? I'm going to zoom back out. What's the expected number of women? So E of x is equal to RA over N. So RA, that's 6 times 10 over 18. That's equal to 3.33. So the expected number of women on the jury is, it's basically 3 1/3, but 3.33. I guess I should use a word instead of equals. Okay, so hopefully these examples are reinforcing your knowledge of hypergeometric distribution. Let's go to example 4. This might apply to our class. In a class of 30 students, 18 have a driver's license, 10 students are selected at random. What's the probability that at least 4 students have their driver's license? So let's look at what we're going to do. So you know this is going to be hypergeometric because as you start picking students out for your 10 selected at random, say if you picked 5 students and they all had their driver's license, well, the probability of the next student having their driver's license will be less because there's fewer students to choose from that have the driver's license. So you can see with this scenario that this would be hypergeometric. It's not always going to be the same probability that a given student has their license. So based on that, we're going to pick our values for the hypergeometric distribution. We know that n is equal to 30. That's the total class size. We know that 18 have their driver's license, and that's what we're trying to find. We want 4, at least 4, so that's going to be our A value. The number of students that have the driver's license is 18. And 10 are selected at random, so that's our sample that we're picking. So there's our values, and we are going to say x, I probably should have said this before we did the variables, x is the number of students who have the driver's license. DL for short. Okay. Now we want, if I want to turn this into a probability statement, for example, if we go back to example 1, right? I said probably x equals 2. Okay. So in this case, it's worded a little different. It's at least 4 have their driver's license. So we want to say probability x is greater than or equal to 4. So more than one value of x. Okay, so if you think about it, we're picking 10 at random, so we'd be looking at the probability of 4 students plus the probability of 5 plus the probability of 6, 7, 8, 9, 10. That's a lot of separate calculations. So this is where you spend 10 seconds and figure out, is it better me to find the direct probability by just adding up the ones I want, or is it easier to find the ones I don't want and subtract them from 1, which is 100%. So in this case, if we want 4 through 10, well, we could do that, or we could subtract the probability of x being 0, 1, 2, or 3, and that's fewer calculations. So that's exactly what we're going to do. So it's going to be 1 minus the probability that x equals 0, subtract the probability that x equals 1, subtract the probability that x equals 2, subtract the probability that x equals 3. And I know that's still a fair bit of work to do that, but it's probably half the work of doing it the other way. So now we're going to do our calculation. So 1 minus. Okay, so in this case, we're looking for students that have driver's license being, in this case, being 0. So it's going to be 18 choose 0 times, so if 18 students have a driver's license, 12 don't. So 12, and we want all 10 of our sample to be from this group. So 12 choose 10 over 30 choose 10. We're choosing 10 students out of our class of 30. So that's the number of potential combinations of 10 students. Okay, and then we do, so that's probably x equals 0. We're going to have, just may set up the template here, that's x, probably x equals 1, probably x equals 2, and then finally this one. Just make sure I have enough room. So this one, just like doing the table, this would be 18 choose 1 times 12 choose 9. So we're choosing 1 student that has their license, 9 that don't, over 30 choose 10. Now it's 18 choose 2 times 12 choose 8 over 30 choose 10. And then 18 choose 3 times, so 3 that have their license, 7 that don't, 12 choose 7 over 30 choose 10. Okay, so I'm going to go right to the, like I did on the tables, right to the final answer. Now the first two are kind of interesting because these are, it's extremely low probabilities for having no 0 or 1 student that have their license. So there's a fair number of digits. So this is usually what I do. 1, 2, 3, 4, 5. Okay, so I don't, when I'm doing these probabilities, I usually say, let's go to 4 decimal places like I did on the tables. That's nice and safe. But if I went to 4 decimal places for this, it'd basically be 0. But I don't really want to show that it's 0 because it's not, it's very, very small. So in this case, I just did a very small number, first one decimal, leading decimal there. And then similar here, we had 0.00. 0. Yeah, in this case we do have 4. Okay, and now it's going to start getting bigger, not by a whole lot, but 0.0025 minus 0.0215. Okay, so very low probabilities anyways. I just put that in there to show that it's not exactly 0, but it's extremely small. Now when I actually go and add these up, or subtract them, whatever you want to call it, I don't actually do this one. Well, I could, but it's not going to have any impact on the 4 decimals that we're actually looking at. So this works out to 0.9759. So very high probability, therefore 97.6% probability that at least 4 students have their license. Okay, so we've seen this before where you're looking for a range of values from the distribution. So it's always in your best interest to be lazy and to pick the one that requires the least amount of work. It only takes 10 seconds to figure that out. Do I want to do 4 or do I want to do 7? Well, obviously I want to do 4, so I'm going to do the indirect. Okay, part B of this was what is the expected number of students to have the driver's license from this situation. So plug in our values, RA over N, 10 times 18 over 30. That's exactly equal to 6. So on average, 6 students will have their driver's license. Okay, and if we had done our distribution, probability distribution, we could just look at the highest entry and it most likely would be 6, but it's a lot easier to calculate with this very fast formula here. Okay, last couple of examples here. These should be fairly quick. Okay, so this would be a typical type of hypergeometric distribution question where you have different colored marbles in a bag and you start randomly pulling them out, and then you're asked questions like, what's the probability of getting 3 blue marbles out of the 5 you take? So those are the types of questions. So this question, a box contains 7 yellow, 3 green, 5 purple, and 6 red candies jumbled together. What's the expected number of red candies among the 5 candies poured from the box? Okay, so reading the question, what's the expected number of red candies? Obviously, that's going to be our random variable. So X is the number of red candies. Now in terms of the variables, our N, that's going to be the total number we could choose from. So you're basically adding up all the different colors. So I have 7 plus 3 plus 5 plus 6. I believe that's 21. So 21 candies to choose from. Our A value would be the number of successes or the number of red candies in total, and that would be 6. And the sample, the R value, we're picking 5. 5 candies poured from the box. So there we go. And this question is not asking for a probability of picking a certain number of red. It's saying what's the expected number. So all we really need is to get those values. So our expected value of our random variable X is going to be RA over N, which is 5 times 6 over 21, which is equal to 1.43. So therefore, one would expect to have 1.43 red candies from the 5 selected. Okay. Now this is an interesting one because unlike the other ones where it was fairly black and white, you had a certain number of this and a certain number of the other thing, okay? Like the students with the driver's license, the students without. What else did we have? The jury, men and women. We also had grade 11, grade 12 students. In the previous examples, this one's different because there's more than just two categories. We have yellow candies, green candies, purple candies, red candies. Now, it still turns into binomial because if you're just looking for red, well, it comes down to red candies and non-red candies. So all the other colors besides red get lumped together into basically the non-red candy group. Okay, so it doesn't matter, it doesn't really matter how many different colors there are or how many of each. You just add them all up, and that's your other that's basically your failure candidates. Okay, now what makes these questions interesting is this could be a multi-part question where first question might be something to do with the red candies, so your random variable is the number of red candies. The next question might be about yellow candies, so your random variable would actually change to x as the number of yellow candies, so you'd have yellow and non-yellow. So that's what makes these questions interesting, is you can ask lots of different types of questions about the different categories, and your random variable will change depending on what you're defining as a success. Okay, last question. In the spring, the Ministry of Environment caught and tagged 500 raccoons in a wilderness area. The raccoons were released after being vaccinated against rabies. To estimate the raccoon population in the area, the ministry caught 40 raccoons during the summer. Of those, 15 had tags. Estimate the raccoon population in the wilderness area. So, there's two ways of doing this. So I'll show you the way using the formula from this lesson, and then I'll show you another method which is, in my opinion, a little more logical, and it basically comes down to the same numbers. So if I'm trying to, this is definitely going to be hypergeometric because as you pick a raccoon, the probabilities will change depending on the status of what happens to the next one. So in this case, we don't know what the population is. That's what we're trying to find. So n equals question mark. Now, the ministry caught 40 raccoons, so that's kind of your sample. R equals 40. Your A value, now your A value is the number of, I guess, tagged raccoons, so that's going to be A equals 500. And this is where it seems a little strange. The expected value of tagged raccoons is going to be 15. Okay, so I'm just going to go ahead and do the formula. Expected value of x. So the random variable x is the number of, I believe, tagged raccoons. That's RA over n. So if I plug in the numbers, I'm going to have 15 is equal to 40 times 500 over n. Okay, so if I multiply both sides by n and then divide by 15, I get n equals 40 times 500 over 15, which is equal to 1333.3. So that would be your expected population, the estimated population. So the estimated population of raccoons is 1333. Yeah, we wouldn't put the 0.3 because it's a living thing. So you would round down in this case. Okay, so that's the official hypergeometric formula to do this. But I think there's a slightly more logical way. So if you do based on equivalent ratios, okay, so we saw here that out of the 40 raccoons that were caught, 15 had tags. So if we looked at the ratio of tagged raccoons, that would be 15 over 40. And that ratio should be equivalent to the entire population. And the entire population, we know we tagged 500. So that's going to be on the top. Because in our sample that we caught, 15 out of the 40 had tags. So in the general population, 500 of the entire population, or N, also has tags. So if you rearrange this, you get we get 15N equals 40 times 500, and then divide by 15. Well, look at that. It's exactly the same formula. So obviously going to be the same answer. So for me, I think this makes more sense to do it this way if you're doing one of these population type questions. And this is a fairly popular type of question to show expected number in an application. So you can choose whichever way you like, whichever way makes more sense to you. So I've got some homework questions to be assigned to you, so have a look at them, try your best, and I'll see you on the next lesson, which will be our Unit 4. Have a great day.